Welcome everyone to live session 2 of Design and Analysis of VLSI Subsystem. The course has been taught by Professor Madhav Rao from IIIT Bangalore, and we have this live session every Tuesday from 7 p.m. to 9 p.m. And the goal of this live session is to solve some questions and discuss some of the concepts which are discussed in the class, right? And yeah, I'm Kailash Prasad, PhD scholar from IIT Gandhinagar. So I am from Nano Electronic Device and Circuit Lab. So we will start today's session. So this is the course layout. So in the last lecture, what we have done is we have discussed about CMOS transistors, right? We have solved a couple of questions on CMOS transistor. We have discussed many of the concepts of CMOS transistor, and we have also discussed the current model, right? How do you define CMOS or CMOS transistors which we have. In this tutorial or in this session, what we'll be discussing about CMOS inverter, and all the questions we'll be discussing are about CMOS inverter. Okay, and there are various other topics we'll be keep covering on various weeks. And if you guys have any questions, any queries, right? So you can write to me in my email ID. I'll be sharing my email ID in the last lecture, right? And I also request everybody to join the WhatsApp group, right? If you have any question, any kind of queries, you can ask over there, right? So that it can get immediately resolved. So okay, I will share the link. I will share the link at the end of the classroom, end of this class. Okay. So let's start the very first question which I have, right? So I want to show you. This question we'll be discussing, but before that, this is how what we think of inverter is, right? So what you do, you provide input as 0, the output will be 1, right? If you provide input as 1, the output will be 0. Okay, so just invert the output. If you write a truth table, right? If input is x, output is y, so the y will be x bar. Okay, y will be x bar. This is what inverter is all about. Okay, and in terms of CMOS, right? When you design this inverter using CMOS, how do you do that? So you take one PMOS transistor. This is how a PMOS transistor looks like. There is an NMOS transistor. Okay, and this will be your Y. This will be of X. Okay. Now the question is, so this is the truth table I have, right? This I understand. Can anybody tell me, okay, how does this particular circuit works? This circuit. Anyone? Anyone has any idea how this circuit works? This is VDD. Okay. This is my ground. What happens when I provide input as 0? Can you tell me? I need answer from you guys.
When actually it is an inverter circuit, CMOS inverter. First one is the PMOS, and the next second one is the NMOS. So when it is 0, then the gate voltage VGS is negative for the PMOS, and there is no gate voltage at NMOS. So PMOS will be on, and the VDD will come to the output Y.
And when I provide 1, then it will be other way around.
One means that it is VDD, then the NMOS will be on, PMOS will be off because VGS at that time is 0 for PMOS, and so that way the ground will come to the output.
Okay.
It is 0.
Yeah, thank you. What he is saying that okay, so if I provide 0 over here, right? So what will be the VGS, or in terms of PMOS, when we talk about we call that as VSG, right? Source to gate voltage. Okay, in this terms, right? What is the VSG? VSG is VDD minus 0. Okay, so this is VDD minus 0. This is VDD. Okay, if VSG is greater than VTH, it means that the PMOS is on. Okay. So in our case, VSG is VDD, which will be obviously greater than VTH. Okay, I'm not told what VTH is over here. We'll be using the value in the when we'll be solving the questions, but VDD is always greater than VTH. The VDD is the global power supply. Okay, and in our case, the PMOS is on. Let us check for the NMOS. So for NMOS, source is this terminal. This is our gate, and this is our drain, right? And in this case, let's see what is VGS. Okay, so in the case of NMOS, VGS is 0 minus 0, right? So this is 0, right? So VGS is less than VTH in this particular case, right? So we say that NMOS is cut off. Okay, NMOS is off, right? So if this is off, this is on. Okay, whatever the voltage we have will come directly to the output node. Okay, so Y will be equal to VDD. And in the other case, when here it is 1, right? So Y will be equal to 0, right? This is a simple concept. Now the question is, so this is clear to everyone, right? I assume this is clear. You just type yes, such that I know. Okay, thank you. So now the question is, what happens if I reverse the yeah? What happens if I reverse the NMOS and PMOS? Okay, so what I do, I make an NMOS over here. Okay, and I do like that. Okay, this is X, this is Y. Can anybody tell me what will happen?
It acts as a buffer.
Act as a buffer. It means you are saying that Y will be equal to X every time.
Yes.
Okay. Do you think that there's any problem in this regards if I design a buffer like this?
Yeah, we face some problem. Sometimes it acts as a bad buffer.
Sorry, it will
Yeah.
be a bad buffer. Okay, then
It will be a bad buffer.
what do you mean by bad buffer?
Bad buffer means not exactly the, if we are giving input as VDD, not exactly VDD we are getting in the output Y or
Okay, so Y,
something like that.
okay, what you are saying that, okay, Y will be not exactly VDD. Okay.
Yeah, yeah. Not exactly X.
Okay, not exactly X. Whatever X you are giving, it won't be exactly. And what is the reason behind that? What is actually happening that you are saying that statement that, okay, Y is not equal to X? Others can also answer, okay? Anybody else? Anyone? Lot of people over here. Okay, so I hope, let me discuss.
We
Yes, please.
when Vn is 0,
Mhm.
that time the V out may not be decreased beyond the threshold, that means point zero 0.03 voltage. That means we cannot, that means the output does not reach the rail to rail voltage. That means it is vary between, same for the, if in is 5 volt output we are getting, this is around 4.7 volt. That means 0. It is act between 0.3 volt to 4.7 volt effective output voltage range. But it basically should be the 5 to 0, whereas we are getting the 4.7 volt to 0.3 volt. That's why you can say this is a bad buffer.
Okay,
This is my logic.
okay. So let me explain in more, more technical manner.
Yeah, for that we can calculate some mathematical operation so that we can get the values.
Okay, okay, okay. So what will be happening over here is you have a VDD. Okay, so this is your ground. Okay, so what we will do, we first take this NMOS N1. Okay, for N1, what we'll be having is the VGS, if you see, right? So this is your VGS, okay? VGS, okay? So to make sure this transistor is on, okay? To make sure this transistor is on, what is the condition? The condition is VGS should be at least greater than VTH. Okay, that's the minimum condition you have. So the thing is, whenever you provide VDD from here, there will be always a VT drop. Okay, please listen me carefully. Right, there will be always a VT drop. Right, the VDD entire VDD cannot come here. Okay, so suppose if you provide 0, okay, not 0. Suppose if you provide VDD from here, right, NMOS should be ideally on, right, which it is. But the thing is, what will be the output node? The output node will not be VDD. It should be at least VDD minus VT. So at most VDD minus VT. That is the value it should have. The Y should be less than VDD minus VTH. Okay. In this case, Y will be equal to VDD minus VTH. Okay. Why I am saying like that? The reason is, suppose Y is a VDD. Okay. Y is a VDD. What will happen to NMOS? Suppose I assume that, okay, it has passed the entire VDD. What will happen to NMOS? Anyone? Do you think that NMOS will be turned on?
Yes, it will be turned, but like NMOS is good for passing zeros.
See, I'm taking a statement that is NMOS is good for passing zero. I'm trying to prove why NMOS is good for passing zero. My question is, if this node is VDD, if this is also VDD, do you think that NMOS is on?
Yes.
Why you are saying so? Because VGS is equal to VG minus VS, right? Here VG is VDD, right? And VS is also VDD. This will be 0, right? And VGS now will become less than VTH. 0 is less than VTH, right? So NMOS is turned off,
Okay, sir. Okay, sir.
right? So that's the reason you say that it cannot pass 1 completely, because if it pass 1 completely, the NMOS will be turned off. It won't be able to pass anything, right? So it's a loop. So the thing is, it should be at least VDD minus VTH. So at most VDD minus VTH, okay? Because there will be a VT drop. That's the reason we say that the NMOS is good at passing 0, but not good at passing 1. Okay, so what we got that if I provide VDD here, okay, in X, the output we are getting is VDD minus VTH. Okay, so this is what we are getting. Now let us see what will happen to PMOS. Okay, if this is my PMOS, this is my VG, okay, this is my VS, okay, this is my VD. See, for this transistor, if I provide 0 over here, okay, earlier what used to happen, this node, so earlier what used to happen was like this, okay, sorry, here, this was VG, this was VD, right, it was always at VDD, okay, and if you provide 0, it is complete on, okay. Now in this case, what is happening?
Drain is in zero potential.
Drain is at 0 potential, right?
Yes,
What you want to do, you want to pull this node to 0 using a PMOS,
right.
right? You want to do that. Suppose if I pull this node to 0, what will happen to VGS of a PMOS or VSG of PMOS? See, this was 0, right? Earlier the case was, if this is 0, this is VDD, my VSG is VDD, right? Now in the case when I'm trying to pull this to 0, the VSG will become what? VSG will become,
Ma-
it becomes 0, right?
Not exactly zero.
It will become
In
0.
out.
No, I'm saying that if hypothetically, if I'm trying to pull it to
Oh,
0,
okay.
the VGS
Yes,
becomes
yes.
0.
Yes,
See,
yes.
if VGS becomes 0, right, now the PMOS is off and that node cannot be at 0 now, right? So actually that is not possible, and that's the reason
Hmm.
this voltage should be at least VTH to make
Right.
sure that your PMOS is on, right? So if you provide 0 over here, what you are getting is VTH, right? And this is the reason why we say that
Yes.
this is whatever circuit I have drawn is a bad buffer. Okay, it is not doing a good job. I am providing a swing from 0 to VDD, and what you are giving me, that instead of 0 I'm getting VTH. Okay, instead of VDD I am getting VDD minus VTH, right? Let me tell you this same example in terms of number. Okay, so I think numbers will be more interesting. Suppose VDD is 5 volt. Okay, VTHN is mode of VTHN and equal to mode of VTH. In our case, what will happen if I provide X, okay? Here we provide 5 and here we provide 0, right? The 5 will be converted to 4 volt, okay? And the 0 will be converted to 1 volt, right? So if you provide output like this, suppose what you have done, you have provided 0, okay? Then you have provided 1. So this was the input. What output will be getting? The output you will be getting will be like this. It will be VTH. The output will be VDD minus VTH. Right. So the amplitude of the output has gone down. Okay. And in the zeroth case, which should be ideally 0, it has gone up. Right. So in that regards, our buffer becomes a bad one. Okay. But the output is, if you have this kind of circuit, it will act as a buffer. That is true. Right. But a bad one. Okay. The output will be this one. Okay. Now the question is, if I want to design a buffer, which is a good one, what should I do? What is the best way to design a buffer?
I have to change the scaling.
Change the scaling.
Yes.
What do you mean by that?
Width of the PMOS. No, no, sorry.
Reducing the threshold voltage as low as possible.
Reducing the threshold voltage. Okay, that's an interesting statement. Right. Now the question I have, reducing the V. Okay. Right. Now the question I have, do I design transistor as a circuit designer? Do I design transistors? The answer is no. Right. The transistors are designed by foundry. Okay, they give you transistor with a certain threshold voltage. Okay, and please note that why we cannot reduce threshold voltage beyond a certain point. Actually, that is a limit set by physics. Okay, there is one term that is called as SS, subthreshold slope. What happens is, if you reduce the threshold voltage, right, your current increases ion, which you want. Okay, the maximum current you want. The problem happens, the off current. Okay, when the transistor is off, it also increases. Okay, I off also increases if you reduce the threshold voltage, right? Suppose if you have a mobile, okay, which is working very fast. Okay, I'm saying that it is working very fast, but the thing is, as soon as you remove the charger, the battery goes down in 1 hour. Do you want that kind of mobile? The answer is no, right? You cannot, you don't want, your battery should last, right? The static power, the leakage of whatever circuit you are designing should be extremely low as possible. So if I have a mobile, right, and you just kept the mobile like that, right, ideally the battery should not degrade. But still we have some leakage. That's the reason over the time it degrades. But the thing is, if you reduce the threshold voltage beyond a certain point, then the leakage will be so high that the leakage, the power consumptions go very high, right? And if you deploy that on your devices like laptop or mobile, it will become extremely difficult for you to manage the power. Okay, so we don't do that. We cannot do that. Do we have any other option? Do we have any other option?
That is, we can. You are asking that we can change in circuitry. In
Circuit
circuit,
just to change. Just
Then actually, the problem is that it is not reaching to the maximum value. That is, it should reach to the VDD, but actually it is not reaching to the VDD. It is when it goes to the VDD minus VTH, and it completely not going to the zero.
Yes.
So cannot capacitor can work to supply the required voltage when it is but how?
Okay, so capacitor. Okay, so that's an again interesting argument. Let us see what happens. Okay,
Yes,
let us see. We have a lot of time. Okay, we will discuss in detail, and please understand,
yes,
analyzing circuit in detail is a uh, great requirement. Okay, so if this is my circuit, okay, and you are saying that I put a capacitor over here. Okay, you say that okay, this node is not reaching to VDD in the normal
yes, yes.
case, right? Do you if
Mm-hmm.
you put capacitor in certain time, it will charge to VDD. That's the argument you have.
No, but actually the output node is not going to that level.
Exactly, right? So the thing is, if the
Yes,
output node doesn't go to VDD, then
then
capacitor
it is
cannot be
not
charged to
possible to.
VDD, right? It can be
Mm-hmm.
charged to only that voltage, what the voltage is actually,
VDD minus VTH.
right? So for
Maximum charge will be VDD minus VTH. Or it, but it can go to the, no, no, it cannot go to the ground also.
it cannot go to the ground also. Yes. It cannot be completely charged, it cannot be completely
Can
discharged.
completely discharge. Yes.
Okay. So again, we do not have this solution also. So actually, we don't have solution. Okay. So I'm just frankly saying that I was just asking you if you can come up with some solution. The only solution which we have is this one. Okay. You put do inverter back to back. Okay, and that is in the CMOS fashion, and this is how we do, right? I design chips here at IIT Gandhinagar, and we have actually a very large team working on chip designing, and the thing is, whenever we want a buffer, we put two inverters back to back, right? There is actually no
Yes, yes.
option for us apart from
Yes, sir.
this.
Yes, sir. It is right.
So you put X, you will get Y with full voltage swing. Okay, so this is our buffer. And please understand why we are teaching inverter in the very first two, three, four lectures. Okay, you might think that inverter is a very small circuit, right? You are designed for designing very large circuit like processors and all. But the thing is, all the basic concepts of VLSI actually develops from inverter. Okay, so if you understand inverter in a greater detail, you can understand any of the circuit in the VLSI design. Okay, so that's the reason understanding inverter in a greater detail is extremely important, right? And that's the reason in NPTEL lecture also we take some time to make sure that you understand all the aspect of inverter in a greater detail. Okay, so yeah, now see, this question we have answered. Okay, what will happen, there will be a degradation in the output. Okay, and the technical term is that the output swing we call it is. Okay, output swing means the maximum voltage minus minimum voltage. Okay, v out max minus v out min, right, will degrade. Output swing will degrade. Okay, and output swing will degrade by how much? So I've said that, right? Y max was how much? VDD, sorry, yeah, VDD minus VTH, and Y mean was VTH. Okay, so the output swing OS we can say, right, will be VDD minus twice of VTH. Okay, so the output swing has been degraded by twice of VTH. Okay, so yeah, this was the first question, which was the basic one. Any questions in this regard? I hope everybody understand this concept. Any questions? Okay, so if we do not have any question, we will proceed to I have 7 questions for today. Okay, so first one was the basic one which I have shared, and apart from that, I have 7 questions. See, the question what it is saying that which of the following is the right way to find the transfer characteristic, that is output versus input plot of a real life inverter, right? So see, the said is a real life inverter. Okay, so now the question is, okay, what is non-real life inverter? Non-real life means ideal inverter. Okay, so let me design the output characteristic for you. So see, this is the ideal characteristic of an inverter. Okay, so if this is VDD, this will be VDD by 2. Okay, this is 0, this is VDD, this will be your V in, this axis will be V out. Okay, so ideal inverter should have a step response, right? Below VDD by 2 input, it should be 1, right? After VDD by 2 input, it should be 0. Okay, but inverter are not ideal. Inverter is not ideal, and because of that, what happens? The characteristic looks like this. Okay, so this is how a real life inverter looks like. Okay, now the question is, I have 7 points over here. Okay, so can anybody tell me that which of the point is correct to design an experiment for finding out this transfer characteristic? Anyone? So anybody knows how this transfer characteristic comes? Anyone? किसी को पता है? I'm not getting answer. Yes or no?
From the DC characteristic of the PMOS and NMOS inverter, from that we can derive the transfer characteristic, that means output voltage versus input voltage graph.
Okay. So for from your perspective, which should be the answer from A to H?
Uh,
So when you talk about DC characteristic, what we are talking about? Which curve we are talking about?
IDS versus VDS, or IDS versus V out.
IDS versus V out.
V out
Okay.
for both N and P.
For both N and P. Okay. So I have two options you can see over here, G and H. Now can you tell me which of the two is correct?
Intersection, I think G.
G.
Just a minute. Both PMOS and NMOS transistor, find all the points. G. I think so. The model value for P in for both NMOS and PMOS and find all the points of intersection. Plot mod ID versus. Both are correct, I think.
Both are correct. Okay.
Yes, multiple values. Mod IDS versus V out means this is talking for PMOS, and ID versus VDS means this is NMOS. I think in that case both are correct.
Okay. Anyone has any other argument? So what C is saying that both G and H is correct. Anybody else?
PMOS transistor,
Maybe I. Yeah.
plot.
Anybody?
Okay.
Okay, so I am not getting answer from anyone. So I believe you're confused. Just one moment. Okay, so the thing is, the H point is correct actually, not the G1. And why? Because when you are plotting V out, so see, VDS and V out are both are same. Okay, so in that respect, both are fine, and everything else is fine. The only difference you can see is IDS and mod IDS. Okay, so when you say only IDS for NMOS and PMOS, for PMOS the IDS will be negative. Okay, when you plot in the same plot, it will come in two different quadrants. Okay, so I will plot this.
Mod ID means we consider the absolute value only, maybe positive. Yeah, right. Sorry, sorry. Okay, okay.
So let me explain. So this will be your ID. Okay, so this will be your output characteristic. Okay, this will be like this. Now what you do, if you don't take mode, this is for NMOS. Okay, this is for NMOS. If you plot for PMOS, how it will be happening? It will be like this. So it will be so this is your VDS, and if the ID will be negative in that regards, and if you say that ID is negative with uh, VDS, so it will not come in this particular quadrant. So if you make ID positive, how does it will happen? It will be like this. Okay, it will be like this if you make ID positive. So you have to make sure that you have the absolute value like this, something like this, right? And how does this particular curve comes? It will be the intersection of all of this. Okay, it will be the intersection, and there will be some intersection over here, and you have to plot like this. Okay, you can see both the curve are same. So what we have done, we have plotted different ID, right? So ID is your drain current, right, versus VDS for different V in. Okay, so this is for different V in. V in means VGS, because what we are trying to do, we are plotting output characteristics. Okay, ID versus VDS. Okay, and if you see, if you plot this, what you are getting this plot, and please note that this plot is uh, this plot is actually derived, and this plot will give you a lot of information in future regarding inverter. Okay, that's the reason this plot is very important. Okay, so this will be your output characteristic, and the answer is in this particular case is H. Okay, all the other points you can see that you won't be able to figure out whether you won't be able to actually plot the final output using any other point. Okay, so that's the question one, right? It was the straightforward. Moving to again a very simple question. Okay, so what is the question over here is when the
So I just want to interrupt. I have a request, not regarding the class. I have a request that can you shift the class before 7 a.m.? Is it possible to start from 5 or 6 p.m.?
not really actually. So the thing is, I'm also an have to take classes at IIT, right? And
Oh,
I am a student over here, right? So the thing is, the academic it gets over at 6, okay, and I have to
oh,
come from labs and yeah.
I understand.
Right. So the thing is, and the PMRF has actually provided only two slots, 6 to 8 and 7 to 9. Okay,
Okay.
so we have to take in these slots too.
Yeah, I understand. Okay, no issue.
Yeah. Okay, so moving to question number two. Question says that when the input voltage V of the inverter, okay, is VDD by 2. So whenever this kind of question comes, the first thing we will do, we'll make an inverter. So this is our inverter. such that we understand, okay, what question is trying to say. So this is your V in, this is your V out. Now what it is saying that V in is VDD by 2, okay, VDD by 2. Then what are the region of operation of the two transistors? Assume that beta P is equal to beta N, where beta is mu n CHW by L, right? Can anybody tell me what are the what is the reason of the two transistors?
Both are in saturation.
Both are in saturation. Okay, I have one answer. Both are in saturation. So which one it is? It is D. Anybody has any other answer? Anybody else? Okay. So there is one more answer in both are in saturation. Okay, so the answer is actually correct. Both are in saturation, right? And why I say so? Let us see that if both are in saturation or not. Okay, so this is VDD. Okay, this is your ground, 0. Okay, so for the first one, right? So if you want to just figure out which reason it is, the first thing which you have to check is if your VGS is greater than VTH or not. Okay, or mode of VGS is greater than VTH or not. Okay, for VGS should be greater than VTH for NMOS, mode of VGS should be greater than for PMOS. Okay, so for NMOS, N1, VGS will be VDD by 2. Okay, and the VDS, okay, what will be the VDS? Anybody? When input is VDD by 2, so you guys have said the answer, right? So answer is correct. I'm saying that the answer is correct. My the question is, why do you say so? Why have you said that both are in saturation? Because for me, to make sure that this transistor is in saturation, I have to fulfill this property. VDS should be greater than VGS minus VTH. Anyone? See, the question has given that beta n is equal to beta p. Okay, so the thing is, if I plot this transfer characteristic, okay, if beta n is equal to beta p, this node will be VDD by 2, the output, okay, when the input is VDD by 2. So that's how you should understand. So the output node is here is VDD by 2. Okay, this is real life characteristic. Okay, not the ideal characteristic. If you plot the ideal characteristic, if you plot the ideal characteristic, this is like this. Okay, if you have VDD by 2, right, and if I say at VDD by 2, what is the voltage? What is the output voltage? Right, you won't have any answer, right, because the output voltage can be from 0 to VDD. Okay, but taking care of the real characteristic, if I plot, I can safely say that okay, it will be around VDD by 2, right? So if it is around VDD by 2, right, so the thing is VDD by 2 will be always greater than VDD by 2 minus something, right? So in that regards, this particular transistor is in saturation, and the same thing will happen over here, because what I am saying that mode of uh, okay, so it will be VSD should be greater than VSG minus VTH. Okay, so VSD is your VDD by 2, right? Should be greater than VSG, again VDD by 2 minus VTH. And this statement will also be true. Okay, in both the cases, the only condition that has to be satisfied is VGS should be greater than VTH. Okay, so generally our threshold voltage doesn't exceed VDD by 2. So we say that okay, the transistor is in saturation. Okay, it generally it happens. It is not always the case, but most of the times you will see like that. Okay, so the answer is NMOS and PMOS both are in saturation. Is that clear for everybody? Is that clear?
Sir, so we have assume only VTS less than VGS. Sorry, VDD like that. Only assuming we do not have idea about VDD VTH value here, no?
Okay, so we have assumed that VTH, right? So VDD by 2. So VDD by 2 is greater than VTH. So this assumption we are making.
Okay, okay.
Okay, so generally it happens because VDD, so for
Yeah,
the older technology, VDD is too large. So VDD by 2 is
yeah,
again too
yeah.
large, greater than VTH, right? But I'm just informing you, okay? This is for information, right? So the thing is, in lower technology, the technology which your mobiles are made up of and your laptops are made up of, in that case, it can happen that the VTH is greater than VDD by 2. Okay, it happens. So in that regards, then this equation won't be valid. But we are just assuming that our VDD is very large. So in that case, VDD by 2 is greater than VTH. So in that regards, if we calculate the equation, both the NMOS and PMOS are in saturation in that regards. Okay.
If this condition is not given Bn equal to beta n equal to beta p,
Mhm.
then what we consider?
Then there is a problem.
Okay.
Okay. Then there is a problem. Then okay, how will you identify? Okay, so there should be some things which should be given to identify, okay, where the transistor is, right? Because why this particular thing is very important. Beta n is equal to beta p. I'm saying that, right? And how have I said here it will be VDD by 2? Can you tell me how have I said that this will be VDD by 2? This statement has only been made because this statement was there. VDD, sorry, beta n is equal to beta p, right? If this statement wouldn't be there, I couldn't have said that the V out, sorry, the V out is equal to VDD by 2, right? This statement I am making, right? This is because, right, beta n is equal to beta p. But why? What happens when beta n is equal to beta p? What happens?
Both the transistor have same size.
Both the transistor, no, both the transistor not have same size, right? Because generally the mobility of both the transistor differs, so the sizes
Sir,
would be
please repeat the question.
okay. My question is, if beta n is equal to beta p, what I am saying, so this is my statement, okay? What I am saying that V out is equal to VDD by 2. My question is how and why I am saying that. Did you get my question?
Yes, yes.
I made the statement, right? But you guys have not asked why you are saying that. You just assume that, okay, it will be VDD by 2. But there should be logical reasoning behind that, right? See, let me explain what happens if beta n and beta p are same. It means the current flowing through both the transistor, the current driving capability becomes same. Okay. When I say that current driving capability becomes the same, right? Now, what you have to assume, because now what you're saying that this is VDD by 2, okay, in the cases, right? If the current driving capability of two of the devices are same, we say that the resistance of both the devices are same, because that's the reason, right? The current driving capability of both the transistors are same, right? So I can approximate this particular circuit like this, okay, only for this particular purpose. It won't behave like this, but in this particular situation it will behave like this, and this is R1, this is your R2, and this is your V out, okay, this is your VDD. And because the current driving capability of both the transistors are same, beta p and beta n are same, R1 is equal to R2, okay. If both the resistance are same, what will be? It will behave like a resistance divider, and the output will be what? Output will be, if R1 is equal to R2.
VDD by 2.
See, that's the reason. Okay, and that is the reason whenever you design an inverter, we make sure that the beta should be same. Okay, the beta of that inverter, the NMOS and PMOS should be same. Okay, so we will equate this in next couple of questions. We will be coming into this particular part, right? But yeah, that is one of the reason behind that. Okay, so the beta, why it should be same? The current flowing, the current capability of both the transistors should be same. Okay, we will see that what happens if current capability of both the transistor is not same. Okay, so I'm just noting down this point, but in coming lectures, and I think in this lecture also we will go through some of the concepts behind that. Okay, so yeah, this is the second question we have discussed. Should we move ahead to the third question?
Yes, sir.
So yeah, see, this is the third question, and again it is a follow-up of the previous question. The question here is, what is the skew of all of this three inverter curve or transfer curve which we have made? Do you know about skew? There are two kind of skew. Okay, low skew. We say that okay, it's a low skew inverter or high skew inverter or without skew inverter. Can anybody tell me?
According to beta value, we can decide about SQ inverter, type of SQ inverter.
Okay. So what do you
If
observe
beta,
from the first curve and second curve and third curve?
for
The
first
ratio of beta P and beta N.
both beta for NMOS and PMOS same for first curve.
There won't be any skew.
No.
Okay. What about the second one?
Beta P is less than beta N. That means ratio is less than 1.
Beta P is yeah.
Less than ratio is less than 1.
Okay. So what kind of skew it is?
Low skew.
What about the third
Next one is high skew. High skew.
beta P is greater than beta N. High skew. So yeah, the answer is correct. Now again my question. My question is, how have you said that beta P is less than beta N? What is your logical reasoning behind that?
With of PMOS and NMOS.
With, sorry,
With of PMOS. If we increase the width, uh, from that we can set the value.
that is fine. But after observing this particular graph, just by looking into this graph, how can you say that the beta P is less than beta N?
Oh,
You might have
this
thought something.
this is shifted left.
Okay. So yeah, that is not a correct answer, right? 15.
No, I understand.
Can you tell me? See, what you have to do, you have to just calculate the VSD of PMOS and VDS of NMOS. Okay, at VDD by 2. So you see, if you provide V in at 1.5 and your final, so VDD is 3. Okay, VDD is 3, V in is 1.5. Okay, now the thing is, what output is coming is 0.33, 0.33. Okay, so it means if I have designed an inverter, okay, and if I provide 1.5 input over here, which is VDD by 2, okay, and here it is VDD, here it is ground. See, ideal expectation when beta P is equal to beta N, what I have said, it should be VDD by 2, it should be 1.5, right? So when it is not, there is no skew, the output should be 1.5, which is in the case of this one, right? If the input is 1.5, output is also 1.5. So there is no skew. Okay, this we agree, right? Because this we have proved in the last question. Now the question over here is the second one. The second one is saying that your output is 0.33, right? It means that there is some skew that we understand, right? Output is not 1.5. It means there is some skew. Now we have to think, we have to understand that, okay, which of the transistors is have more strength and which one has lesser strength, right? My simple question or simple analogy to understand this will be which transistor will make it go down and which transistor is trying to pull it up, right? If strength of both are same, it will be at VDD by 2 because VDD will be equally divided. In this particular case, which transistor is faster? Which transistor is faster in this case?
NMOS will be faster. That is, it is pulling down the for
Okay,
the
so
second.
the NMOS is faster, you are saying, or PMOS?
Yes, because no, because it is pulling down the output. Because applying a 1.5 volt at input, we are getting 0.33 at the output. So it
Yes.
is
So NMOS
pulling down.
has more strength, right? NMOS has more
Yes,
strength,
NMOS are the most strength.
right? So when you say that, okay, it has more strength, it means it has more current driving capability, right? So current driving capability is actually defined like this, okay? So actually defined by beta because the current is nothing but beta by 2 VGS minus VTH whole square, okay? And you can see that VGS and assuming VTH is also same, in this particular case, VGS and VTH of both the transistors are same, okay? The only thing which is differing should be beta. Okay, and that is the reason we are saying over here that beta n is greater than beta p, right? Or whatever we have said that beta p is less than beta n. Okay, it is a low skew inverter, and the same you can identify from here. Okay, so what you have to calculate, what I have said that VSD. Okay, so if you see the VSD of NMOS, sorry, VDS of NMOS, so VDS of NMOS is 0.33. Okay, and VSD of PMOS is equal to how much? Is very high. Okay, so this will be 3 minus 0.33. This will be 2.67. Okay, so whichever transistor which has lesser VSD has higher driving strength in that regards. Okay, so you can prove my argument over here also. This everybody understood why I'm saying this. Solving this kind of question by remembering is one job, right? But the thing is, when you want to be a good designer, right, you should understand that, okay, by changing what I'm getting a low skew, by changing what I'm getting a high skew. Okay, so ideally, typically in all the circuits, we want that beta should be beta n by beta p should be 1. Okay, so beta n should be equal to beta p. But there are various applications where you might want a low skew and high skew inverter, right? So if you don't understand by changing what parameter I am making my transistor low skew or high skew, you won't be able to design the circuit properly, right? So here what I'm saying that, okay, if I have a low skew transistor, beta n is greater, right? How do you make beta n greater? Okay, I have lot of things, okay, mu n COX W by L. Okay, so mu n cannot be varied because that's a technology parameter. COX also cannot be varied. Okay, the only thing as a digital designer which we can vary is W and L. Okay, also in digital design, so this is the thing which I'm saying, L is also kept as fixed. Okay, it should be minimum. Okay, so if it is 180 nanometer technology, L should be fixed at 180 nanometer. The only parameter that is to be varied for you is W. Okay, so if you want to make a low skew inverter, you just increase the W of the NMOS. If you want to make a high skew inverter, you just increase the W of the PMOS as compared to the NMOS. Okay, if you do that, uh, so the thing is you'll be able to make low skew and high skew inverter. Okay, is that clear, everybody? Should I proceed ahead?
Sir, how we call this low SQ based on the value of this output voltage or based on
So,
this beta n value?
yeah. So why low? Low means it is skewing to the lower voltage.
Okay. If
Right?
it is
The output is skewing to the
skewed
lower
to
voltage.
lower voltage, then it is called low
It is
skew based
the
on
output.
output value.
Exactly. Output. The
Okay.
term low
Okay.
skew comes from there. Right? The definition comes from the beta.
Okay.
Okay. Anybody has any question in that regards? No questions. Okay. Very silent class. Okay. So very simple question. Anybody want to tell me what is the formula of V threshold, VT? VT. So this is the threshold voltage of inverter. Okay. I think in class sir has taught this. Anybody remembers? If you don't remember, I will obviously say. Right. So this will be VDD plus VTP. Sorry, VDD plus VTP. Then under root gamma plus VTN upon 1 plus gamma. Okay, where gamma is beta p by beta n. Okay, this is, everybody agrees with this formula. So this is the formula of VT, threshold voltage of inverter, right? Or this is the point at which the inverter trips, right? If you just make if you ramp the input from 0 to yeah, just keep on increasing at VT, the output will become 0, right? In 0 the output is 1, and as you keep on increasing from 0 to as you reach the VT and beyond that, the output will flip. Okay, that's the reason threshold voltage is important. Okay, so in this particular case, we are just using the long channel equation. So this is the long channel equation, we say, right? If you put all the appropriate values, the V threshold you will get, how much you will get? Anybody wants to solve? Anybody? See, you just have to put the formula. Okay, beta p by beta n, how much it is? So beta p is so beta p by beta n will be mu n cux, mu n cux w by l, WLN, sorry, WLP, mu p cux WLP by, so this will be beta p, and when by beta n, this will be mu n cux Wn by Ln. Okay, so cux will be same, so it will be cut down. Here in the case of mu p and mu n, right, you see, okay, so you don't cut down mu p because this value has been given over here, right? So this is nothing but 100 by 200. So this will be 100 by 200. Okay. WP by LP, WN by LN, right? So LN and LP are same, so it will be cut. So WP by WN, WP is 720, WN is 180. Okay, 720 by 180, this will be 4. Yeah, 18 4 is 72. And the eventual value will come at 2. Okay, so beta P by beta N is nothing but 2. Right, so gamma is equal to 2. Right, if you solve everything, the answer you will get is 1.689 volt. Okay, I'm not solving over here because this is just a mathematics. Okay, but the thing is, why this question is important? Okay, so the thing you should understand over here that, okay, the trip point or the threshold voltage of inverter, it is depending on what things. Okay, the very first thing which it depends is on VDD, right? More the VDD, higher the trip point. Okay, then the second thing it depends is on the threshold voltage of NMOS and PMOS. Okay, and the most important parameter over here is gamma, right? Beta p by beta n, right? So gamma is above also and below also. So it is providing a effect, right? So increasing and decreasing gamma can increase or decrease beta, right? And you can find an optimum point over here. Sorry, increase and decrease VT, and you can find an optimum point over here. Okay, so that was a very numerical question. Okay, I will move ahead. Yeah, very simple question again. Which of the following transistors are in saturation? Assume that all the transistors are perfectly identical. Perfectly identical means width, length, Vt, everything is same. Which of the transistor is in saturation? Quickly, I want quick answer from you. Anybody wants to answer? Random guess. You can type. Okay, so we have a lot of people over here. Archita, Shweta, Aishwarya, Anirudh. Anybody? Which of the transistor you think is in saturation? I guess nobody is answering. So let me tell you. How do you approach this particular problem? Okay, second and third. Okay, second and third. Okay, so I have at least one answer, right? Let us see if that is correct or not. But anybody else want to answer? See, for transistor to be in saturation, what do you want is VGS should be greater than VTH and VDS should be greater than VGS minus VTH. Okay, so that's
One will be saturation
okay.
in one.
I have one more answer which is only saying one, right? The second answer was 2 and 3. Any other variation? Let us see. Okay, let's start with N1. For N1, the VGS of this particular transistor is what? VDD minus there is a voltage Vx, okay, which we don't know. Then VDS, this is also VDD. Okay, so here it will be VDD minus Vx greater than this equation. Let's see if it is satisfied or not. Again, VDD minus Vx minus VTH, right? So Vx and Vx are cancelled, right? VDD should be greater than VDD minus VTH, right? Which is a true statement, right? VDD is always greater than VDD minus VTH, right? So the thing is, VDS is greater than VDD. Uh, VDS is greater than VGS minus VTH, and we are also saying that VGS is greater than VTH. Okay, because if that is not the case, then the transistor won't be on. Okay, so that should be there. Okay, so the thing is N1 is in saturation. That is a correct statement. Okay, because the statement which we have derived, it says that N1 is in saturation. Now the question is, what about N2? Okay, so let us go back to N2 and follow the same equation. Okay, for N2. Now here it is Vx, here it is Vy. Okay, if you see over here, and so VGS, okay, so Vy, VGS, and here it is VDS minus, sorry, VDS and VGS minus VTH. Okay, so this will be VDD minus Vy. Okay, and this is VD, yeah, so this will be Vx minus Vy minus VTH. Okay, so Vy will be cancelled. Now here it is VDD. Okay, here it is Vx minus VTH. Now the question is, right, is VDD greater than Vx minus VH? VTH. Everyone, please tell me if this statement is correct or not, whatever I'm making. So from here it looks like, right? Vx is VDD is greater than Vx minus VTH. But there is a catch, okay? So this Vx, and if you see the VTH, okay? So you actually don't know the value of Vx and Vy over here. Okay, we are just deriving the equation, but here we don't know what value it will actually take, the Vx and Vy. Okay, so that you have to take care. Okay, and the thing is, the Vy should be at least such that this transistor is in on. This transistor is on. Okay, so yeah, so in this particular case, if you see the VGS, VGS will be your VDD minus Vy. Okay, and VDS will be Vx. Okay, so okay, I think I have done its other way around, so that's the reason it is coming incorrect. Okay, so VDS is Vx minus Vy. Okay, there it is VDD minus Vy minus VTH. Okay, yeah, so that was I was saying that, okay, how it can happen. Okay, now Vx, and here it is VDD minus VTH. Okay, what is the chance that Vx is greater than VDD minus VTH, right? So Vx should be at least VDD minus VTH to make sure that this transistor is on, because that's what we have understood. Okay, the thing is, it should actually it will go below VDD minus VTH, and because there are multiple transistors in stack, right? And this condition may not satisfy. Okay, and that is the reason we will say that this will be in linear region. Okay, if it is exactly VDD minus VTH, so it will be in the border of saturation. Okay, if it is exactly, but in all rest of the cases, it will be in linear region. It won't go beyond that. Okay, and the same will happen to N3 also. Okay, if you see, this will be VDD, right? This is 0, right? This is your Vy, and if you again see the Vy, that will be your VDS, right? And it will be VDD minus 0, right? Vy cannot be greater than VDD minus 0. Okay, Vy cannot be greater than VDD, right? Because whenever the voltage will come here, there will be some drop over here, some drop over here. So again, this transistor will also be in linear region. Okay, so this is in linear region. This transistor is also in linear region. The only transistor which is in saturation region is the first one. Have you guys understood this, or there is a confusion in this? Did you guys understood?
Yes, yes.
Moving to again a very simple question. It's extremely simple. You should quickly answer in 2 seconds. What should be the W by L equivalent of this particular circuit? This has been discussed in class. Okay. If I make this particular stack as this one, what will be the equivalent W by L? This, see, this is the W and L of transistors are given. N1 has 180 nanometer.
W is 4.
W is what?
4 for all the 3 M1, M2, M3.
No, I didn't.
Sorry, it is 3. It is 3. W is 3 here.
W is 3. Okay. What about L? Okay, you are saying W.
L.
Yeah.
I mean, I'm saying that the ratio is
W by L
3.
is 3.
3.
Okay. you're saying that it will behave like W has become 3W.
No, no, not that. If L is 65 nanometer technology, you are saying, no?
So see, W and L is same, right? So W is 180, 180, 180. L is 180, 270,
Acha,
540. What will be the equivalent W by L?
acha. L is not same for all the three.
L is not same. You can give me the exact number. Anyone has answer? What happens when the transistor are in series and have the same gate voltage? Is there any change in W, or we can have an equivalent W and L? Can we have? Okay. So the thing is, yeah, this would have been discussed in class. I will just directly quote the class. Okay. You should go and see the lecture slides. That is extremely important before coming to the tutorial section. What happens is it will behave because all the transistors are in series, right? The current will be divided. Okay. So it will behave like so when the current is divided, when the current is less. Okay, that's you have to understand. Okay, so I will just give you rough overview what actually happens. So this is mu n cux w by l. Okay, uh, it will be vgs minus vth multiplied by vds minus vds square by 2. So this is your current equation. And what happens when I say that three transistors are in stack? Okay, so the current will reduce. Current, how the current can be reduced? Either W goes down or L goes up. Okay, so in the class it has been taught that whenever we have a stacking of this transistor having same gate voltage, if you solve the equation, right, you will get the equivalent of this as W by L equivalent will be, because all the transistors have same W, so it will remain same W, but it will be L1 plus L2 plus L3. Okay, so it will be 180 nanometer divided by 180 plus 270 plus 540 nanometer. Okay, it's like that. Do you guys remember this from class? Did you understood what I've done? See, I've roughly told you the concept behind it. If you exactly solve like the class, you will get W by L equivalent equal to W by L1 plus L2 plus L3. If they have three different L, if they have same L, it will be W by 3L. Okay, so the answer was if what if it would happen if L, all the L's were same, it wouldn't have been 3, rather it would have been 1 by 3. Okay, 1 by 3. The answer would have been right. So how do we arrange this particular transistor such that, so my next question is that only. Okay, so I don't have that question here, but I will frame quickly and you just tell me that how do I have an equivalent, okay, what should I do with N1, N2 and N3 just to make this as 3 W by L? It means I have to increase width 3 times. What should I do? Assume that L1 is equal to L2 equal to L3, W1 equal to W2 equal to W3.
Connect all in parallel.
Connect all in parallel. So that's the correct answer. Okay. So what you should do, you should connect all the transistors in parallel.
Parallel connection, yes.
What you do, you have this. Okay. Again, one more. Okay. So this will give you a equivalent transistor with 3W. Okay. So this is if the width is multiplied 3 times. So now you can understand that in this case, the L is multiplied by 3 times. Okay. Last question for today. Okay. A very simple one again. Which of the following are the reasons for using both PMOS and NMOS transistor in parallel in a pass gate, right? Or transmission gate, what we say. Okay. So the thing is, transmission gate looks like this. Okay. So this is how it is. This is PMOS, this is NMOS. If this is X, right? Here it is Y, right? And what is the reason to have both of them in parallel? This I think we have already discussed in one of the question, right? You can quickly tell me the answer.
Actually, both are connected in this fashion to completely pass the zero logic zero or logic one whatever. If input is high, then to pass the input of the output side, then
Yes.
we require the PMOS,
Yes.
and when it is zero, then we require the NMOS.
Mhm.
The advantage of this structure is that it actually enhances the speed because for VGS minus VT, when it is we are transferring zero, then from VGS from VDD from VDD or VDS from VDD to zero.
Yes.
Um, just a minute. When we are transferring the zero, that means the NMOS will be on, and for VDD for VDD minus VTH voltage, that the PMOS will be also on. So for the first VDT to my VT from VDT to VT, both the path are on. So the transition is fast. Same
Mhm.
case. Uh, Same thing is happen when we are passing the one also. Then PMOS will be on for whole time, and NMOS will be on for up to VTH.
Okay. Yeah. So I understand, right? What you are saying
Yes,
is,
yes, yes. Actually, the notations I have, no, I have forget the notation. What is the maximum level that PMOS and NMOS will reach?
okay.
And that is the main problem.
Okay. So, okay. So, what will be the answer among this? So, whatever you have
Okay,
said, can
among
you tell me?
this, just a minute. I cannot. Just
So, the first statement is without PMOS transistor, it is impossible for the output voltage to reach VDD, right? So, that's the correct statement, right? So, that was one of the reason, right? So, if you want to pass VDD, you need PMOS.
yes, yes.
And same will go to the sixth one. Without NMOS transistor, it is impossible for output voltage to reach zero.
Yes.
Okay. So, 1 and 6. Okay. 1 and 6 are the answer for this particular question. Right. Now, I have a quick question. If I would have this PMOS, okay, and if I pass 0 and here it is VDD, what will be the output? What's
Output will. Oh, sorry, you are giving me VDD. Output will be the zero.
output will be 0?
Yes, it will be past the low logic.
It is not able to pass the low logic, right? PMOS cannot pass the low logic.
Oh, it is PMOS. Sorry. I am. No, no. It is not. It is not able to pass the zero there, but the output will reach to VT up to VT threshold voltage. Yes.
Output will be VTH, right? That's it.
VT. Yes.
Okay. Now I have
Uh,
a follow-up question. Okay. So now if it is an
yes.
NMOS and here it is VDD and the input is also VDD, so what will be the output?
VDD minus VT.
VDD minus
Output
VDD.
will be VT. Yes.
Okay. So this is correct. So I will just take some more question in the follow-up one. Okay. So I will make like this. Okay. So like this. This is my NMOS, three NMOS. Okay. VDD, VDD, VDD. Okay. and here it is VDD. So what will be the output? What is the maximum voltage you will observe over here?
VDD minus VTH.
It will be VDD minus
Minus VTH
or 3 VTH.
VTH. Yes, that is the question.
What it should be? It should be VTH or 3 VTH. VDD minus VTH or VDD minus 3 VTH. Okay, let me simplify this for you. The answer is VDD
It
minus
is VDD minus VTH. It is
VDD minus
actually it actually depends upon the gate VDD. That is the gate voltage.
VTH.
What is the out? Yes,
That is
it is
correct.
VDD.
If you have any sum, so here you will get VDD minus VT, right? But the gate voltage again VDD, so here also you will get VDD minus VT. Okay, and here is also VDD, so you will get VDD minus VT as an output, right? But when the output will start degrading, so I have that kind of circuit also. Okay, so let me just design it for you. This is VDD. Okay, the output is connecting to the gate voltage. Okay, and this is VDD, this is also VDD, this is also VDD, right? In this case, the output will be
So VDD minus 3 VTH. So the last out.
3 okay? Because here it will be VDD minus VTH,
Yes.
here it will be VDD
Like
minus twice
minus 2 V twice VTH.
VDD minus 3 VTH,
Which
right?
type of connection it is called? It is
Sorry, what kind of connection?
the name of the it is stack connection. It is called the
Yeah,
stack.
you can say that, right? So we generally don't use this kind of connections, right? But yeah, in
Yes.
many a times in circuits, you might require to connect this to gate of this transistor. Okay, so when we will design larger circuits, we will come back to all of these small things, right? So every concept which has been taught in class, every concept which I am discussing over here, you should just keep in mind. Okay, so when we will design larger circuits, all these concepts will be useful for you. Okay, so see this kind of question, whatever I have said, right? Any company you go, the first question they will be asking this kind of questions only. Okay, so the initial questions which I have discussed yesterday in the last class, some of the questions which I've discussed over here, these are the basics you should know whenever you are designing. And whenever you are solving some question, right, or whenever you are saying an argument, okay, the beta will be low skew, so the circuit will be low skew. There should be a why in it, okay? Why it is low skew, and you should have a definite answer that okay, this is the reason why it is low skew. And if I want to make any circuit low skew, I have only this kind of possibility. These are the things I cannot change. This thing I can change, right? You should have absolute clarity whenever you're designing a circuit. Okay, so I had this much questions only for today. So this is the link to WhatsApp group. You may want to scan and yeah, you just join it. Or maybe I will share this link. I need to check if I can share or not. Okay. So, do you guys have any questions? Any questions? Okay, link. Yeah, link. Just give me a minute. Okay, so here is the link. Please join the group, right? If you have any question, you can ask. And I put a gentle reminder over there. And the thing is, if you have your friends who have not registered for the course, still want to understand VLSI, and yeah, because I discussed some of the concepts, okay? Um, Please share this particular link with them, okay? And encourage all the people to join these classes, okay? So NPTEL is trying hard to make sure that the learning should be more interactive. So they have assigned us, the PMRF students, to take the classes. It will be only fruitful if more and more students join, right? We are here to discuss any kind of doubts which arises in this particular course, okay? And on the personal note, if you want any kind of guidance regarding the VLSI design, what kind of future you have, if you want to go for research, right, you can contact me directly or my email, okay? So thank you for joining today's class. Yeah, that's all. We'll be signing off for today.